Good day, everyone. I am Christy Canete, representing my team with Christine Panti, Althea Navarra, Kerby Rubinas, Brian Bautista, and Marion Vicencio, under the guidance of Dr. Lessandro Garciano and Engineer Luis Lopez. And I am here to present our research entitled Establishing the Characteristic Bending, Compressive, and Shear Strengths Parallel to the Fiber of Bambusa blumeana. The demand for sustainability in development and human activity has increased throughout the years, focusing mainly on environmental sustainability, economic sustainability, and social sustainability. Simultaneously achieving these demands is a challenging task as engineering supports economic and social sustainability, but it can be detrimental to the environment. Thus, the application of sustainable raw materials in engineering needs further exploration. Bamboo is widely known as a sustainable building material due to its natural strength and flexibility. It is used in traditional houses in Asia as it is abundant in tropical rainforests. In the Philippines, houses in rural areas utilize bamboo as a substitute for timber as it is cheaper and easily accessible. However, the use of bamboo as a construction material in the Philippines is still limited due to the lack of governing codes and design guidelines. Bambusa blumeana, locally known as kawayan tinik, is the most economically important and commonly used Philippine bamboo species. It has been used in construction, concrete reinforcement, furniture making, and fences. This study aims to analyze the characteristic bending, compressive, and shear strengths parallel to the fiber of Bambusa blumeana in its air-dry condition. It also determines the correlation of its geometric and physical properties to its mechanical properties using simple linear regression. A total of 263 samples were sourced from Base Bio Innovation Center, 70 of which were tested for bending strength, 93 for compressive strength, and 100 for shear strength. Each bamboo sample underwent visual inspection to check for initial defects prior to testing. The geometric and physical properties were measured using a digital vernier caliper. The length measurements of the samples were determined as indicated in the test protocol. For the samples tested under compressive and shear strength, the length of the sample is the lesser of the outer diameter or 10 times the wall thickness. On the other hand, the test protocol requires a minimum length of 30 times the diameter for samples tested under flexure. The outer diameter was obtained as the average of two perpendicular measurements made across opposite ends on the outer surface of the sample. The wall thickness of the samples was calculated as the average of four measurements taken around the circumference of the column at angular spacings of 90 degrees on both ends of the sample. The mass of the samples were obtained using a weighing scale in kilograms and grams. The cross-sectional area and mass per unit length were calculated using the equations as shown. Each bamboo sample in the testing machine is applied with a continuous and uninterrupted load such that the failure is reached within 300 plus minus 120 seconds. Failure in less than 30 seconds were discarded from the analysis. The maximum applied load and failure modes were recorded in each test. The bending tests of the bamboo columns were performed using a universal testing machine with a load rate of 18 millimeters per minute and using a 4-point loading bending test setup. The flexural properties of bamboo consist the ultimate bending moment, bending strength parallel to the fibers, and tangent bending stiffness of the column, all of which were calculated using the equations as shown. For the compressive tests, each sample is placed on the UTM, such that its axis is aligned with the loading axis of the machine as prescribed by the test protocol. The compressive strength parallel to the fibers of the bamboo was calculated using the equation as shown. For shear tests, the samples were applied with a typical loading rate between 0.15 to 0.30 millimeters per minute using the setup prescribed by the test protocol. The specimen is supported at its lower end over two opposing quadrants and loaded at its upper end over the two other opposing quadrants, which will induce shear failure on four shear plates. The shear strength parallel to fibers is calculated using the equation as shown. After the mechanical tests were performed, a piece of the bamboo sample was extracted near the area where the failure has occurred. The test pieces were weighed and measured to obtain the initial mass, dimensions, and volume of the test piece before they are oven dried for 24 hours. After oven drying, the oven dried mass of the test pieces were measured. The density and moisture content of the samples were calculated using the equation as shown. The characteristic strength values for each mechanical property were calculated using 5th percentile based properties with a 75% confidence evaluation. The basis for evaluation of non-parametric data is AS/NZS 4063.2 fitted in accordance with the bamboo samples. The characteristic strength value was calculated using the equation as shown. For our results and discussion, multiple failure patterns existed for each testing made onto Bambusa blumeana. The bending failure modes were categorized in 4 types. Type 1 is the ideal failure, existing in the middle, right into the constant moment zone. Type 2 is where the failure mode occurs in the point of load application. Type 3 failure mode happens in the constant moment zone, where loading was applied extending to the middle. And type 4 is a total collapse of the bamboo column. For compressive tests, 3 failure modes were observed, which are splitting, crushing, and combined splitting and crushing failure. Specimens with combined splitting and crushing failure were observed to have splits occurring along the crushing zone. In terms of shear failure, the specimen failed on either 1 or 2 shear failure planes, with 64% of the total tests failed on the 1 shear failure plane and 34% failing on 2 simultaneous planes. The geometric properties determined for each mechanical test through measurement using a vernier caliper with 0.1% precision are listed in the tables as shown. Other physical and mechanical properties were also determined. However, it should be noted that for bending, the values were normalized at 12% moisture content. Average strengths were recorded at 92.63 MPa for bending, 70.67 MPa for compressive, and 11.44 MPa for shear strength. It could be observed that Bambusa blumeana is most resistant to bending failure and most vulnerable towards shear failure. Simple linear regression was used to assess the relationships between the geometric and physical properties to the mechanical properties of bamboo. The performance of the model was determined based on its coefficient of determination value, classified in 3 levels of correlation. The results indicate that the bending strength has a strong correlation with density, while the compressive and shear strengths have a moderately strong correlation with moisture content and density, respectively. The geometric characteristics and mass per unit length of the bamboo shows weak correlation, which indicated that all 3 strengths are relatively independent of these properties. Using the ISO 12122-1 standard, the computed characteristic strengths were recorded at 55.90 MPa for bending strength, 46.63 MPa for compressive strength, and 5.15 MPa for shear strength. Since the characteristic strength is computed based on ranking and concentrates on the lower limit or 5th percentile of all the data values, it is expected that the characteristic values are lower than the average mechanical strengths. This table shows the computations for the characteristic strengths where the multiplier is equivalent to 1.94 for the bending and compressive strengths and 1.85 for shear strength, varying based on the number of samples. The obtained strength values of Bambusa blumeana were compared to the reference values for visually stress-graded unseasoned structural timber of Philippine woods, considering the high strength group at 80% stress grade from the NSCP. It can be observed that all mechanical properties studied have far larger values than the indicated reference design capacities. This indicates that Bambusa blumeana is a viable alternative to wood as a construction material. To synthesize our study, Bambusa blumeana has a high bending strength as compared to its compressive and shear strengths. There is a strong correlation between the density and bending strength, while there is a moderately strong correlation between the density and shear strength and between the moisture content and compressive strength. Both the average and characteristic strength values of bamboo are greater than the high strength group of structural timber with 80% stress grade. Therefore, Bambusa blumeana can potentially be a substitute to timber as a construction material. For our recommendation, it is recommended to establish the characteristic tensile strength of Bambusa blumeana using the ISO standards. The relationships between these mechanical properties could also be examined such that determining one property could lead to prediction of the other properties. Once again, this has been Christy Canete, representing my team with Christine Panti, Althea Navarra, Kerby Rubinas, Brian Bautista, and Marion Vicencio, under the guidance of Dr. Lessandro Garciano and Engineer Luis Lopez, presenting our research entitled Establishing the Characteristic Bending, Compressive, and Shear Strength Spiral to the Fiber of Bambusa blumeana. Thank you very much.